For the last decade, wireless engineering has been preoccupied with a single objective: increasing the peak theoretical speed limit. The Wi-Fi 7 standard, known technically as 802.11be, represents the peak of this approach. By utilizing 320 MHz channels and 4K QAM, it achieves what the IEEE calls extremely high throughput. However, a high speed limit does not prevent congestion. When multiple routers and hundreds of devices occupy a dense environment, raw throughput degrades as overlapping networks compete for the same airtime. The IEEE 802.11bn standard marks a pivot towards ultra-high reliability, moving the engineering focus from peak speed to active traffic coordination. Wi-Fi 8 modifies the MAC and PHY layers to replace the uncoordinated contention of previous standards, with a scheduling system designed to manage the radio frequency environment as a deterministic fabric. This chart outlines the evolution of Wi-Fi standards. While previous generations focused on expanding capacity and performance, the Wi-Fi 8 capstone establishes a specialized era of wireless reliability. The primary constraint of legacy architecture is how isolated basic service sets manage the medium, relying on a mechanism called airtime contention. In these systems, each access point operates independently. To send data, they effectively shout over neighboring signals to secure a gap in the crowded spectrum. This uncoordinated behavior creates overlapping signals and interference. Regardless of a router's maximum bandwidth, these collisions force the network to drop packets in an unpredictable pattern. For emerging technologies like autonomous robotics or spatial computing, a connection that drops 10% of its packets is unusable, regardless of its peak speed. To address these failure states, the IEEE 802.11 Working Group formally established the 802.11bn Task Group. The task group moved away from ideal condition speed metrics, instead building a success criteria based on worst-case scenario performance. This document specifies the target metrics. The first mandate increases throughput by 25% in challenging signal conditions, measured at weak signal-to-interference and noise ratio levels. The second mandate targets a 25% reduction in packet loss during transitions between overlapping access points. Improving the signal edge and minimizing transition loss ensures that mobile devices maintain their connection even at the weakest boundaries of an access point's coverage. The third mandate requires a 25% reduction in latency for the 95th percentile of the network's latency distribution. By measuring success by these specific connection failures, the IEEE forces the standard to prioritize network stability over theoretical peak speeds. This distribution curve maps the travel time of every data packet moving across a network. The peak is the average latency. Wi-Fi 7 manages this efficiently, delivering packets under 10 milliseconds. The vulnerability lies here, in the long tail of the curve. This represents the worst 5% of packets, those delayed by interference or congestion. This 5% tail is what causes stuttering in AR headsets, lag in cloud gaming, and timing errors in industrial machinery. The 802.11bn amendments to the PHY and MAC layers re-engineer how the network manages this congested tail. When ultra-high reliability protocols are active, they compress that long tail, shortening the delay for worst-performing packets by 25%. The result is deterministic latency, a mathematical guarantee that data arrives within a predictable timeframe. Establishing deterministic latency shifts Wi-Fi from a best-effort medium to a reliability standard capable of supporting wired-grade infrastructure. To achieve this predictable timing in a crowded building, the network must actively manage how different routers interact. The mechanism for this is multi-AP coordination, the primary MAC layer innovation of Wi-Fi 8. Previous standards relied on access points guessing when the spectrum was clear. In Wi-Fi 8, access points communicate directly to coordinate their activity. This allows adjacent routers to jointly schedule their transmissions. They act as a single collaborative system rather than independent competitors. By sharing medium resources and joint scheduling, the routers allocate airtime mathematically. This removes the random contention that causes latency spikes. The standard also introduces improved in-device coexistence, which handles temporary outages when a device's antenna is shared with Bluetooth or ultra-wideband radios. By replacing independent guessing with synchronized scheduling, the network neutralizes interference before it can degrade the connection. The network must maintain this stability even when the client device is moving across a large physical venue. In traditional handoffs, a device must break its connection with one access point before authenticating with the next, often dropping data packets at coverage boundaries. The 802.111bn standard addresses this by implementing single mobility domains, allowing the network architecture to treat multiple physical access points as one unified entity. The device no longer negotiates handoffs. Instead, the network infrastructure passes the connection along in the background as the device moves. This results in the required 25% reduction in transition packet loss, creating a once-connected, always-connected state. These domains ensure that mission-critical systems, such as automated factory robots, remain perfectly synchronized with their control servers while in motion. The engineering goals of 802.11bn are designed to meet the deployment requirements of the 2028 industrial landscape. Smart factories, logistics hubs, and hospitals are prioritizing this standard because their operations are becoming increasingly dependent on mobile automation. Autonomous guided vehicles and collaborative robots require microsecond precision to operate safely alongside human workers. They cannot tolerate even minor latency spikes or dropped packets. As edge AI becomes more prevalent, these devices must continuously offload processing tasks over local wireless links without interruption. This level of reliability transitions Wi-Fi from a supplemental convenience into the primary communication backbone required to synchronize automated, AI-driven enterprise operations. This graphic shows the timeline for 802.11bn. The working group finalized Draft 0.1 in September 2024, with the path leading to final workgroup approval in March 2028. The task group has already resolved over 1,800 technical comments regarding issues like channel access and coordinated spatial reuse. Modern industrial and spatial computing applications prioritize a high-reliability traffic system over the raw increase of theoretical speed limits. By engineering the MAC and PHY layers specifically for the 95th percentile, Wi-Fi 8 manages the physical constraints of radio frequency contention through mathematical coordination. Wi-Fi 8, the ultra-high reliability standard, establishes the deterministic fabric required to connect the next decade of spatial computing and machine intelligence.